Survey telescopes like the existing Rubin Observatory for the southern sky or the planned Argus array for the northern sky are sensitive to reflected sunlight from interstellar objects that are larger than our biggest rocket, Starship. Namely, they are more than 100 meters in diameter. Fortunately, we can also discover much smaller interstellar objects by using the Earth's atmosphere as a detector. When a 3-meter sized object collides with Earth, its friction on air generates a meteor fireball with an energy output comparable to the Hiroshima atomic bomb. Such an explosion is easily detectable by the US government satellites, which are monitoring Earth routinely for the heat emitted by the launch of ballistic missiles from adversarial nations. When deemed unclassified, the meteor fireballs detected by these warning systems are reported in NASA's CNEOS Fireballs catalog. Yesterday, I co-authored with my postdoc, Richard Klute, a new paper that reported the discovery of 2 meter-scale interstellar meteor candidates in the CNEOS catalog. By exploiting an empirically calibrated uncertainty model from 2025, we have found 2 events that robustly exceed the escape velocity from the solar system. CNEOS 22, detected on July 28, 2022, over the eastern tropical Pacific Ocean, exceeds escape by 8.7 standard deviations. And CNEOS 25, detected on February 12, 2025, over the Barents Sea in the Arctic, exceeds escape by 5.5 standard deviations. The diameters of both objects are 1.8 meters for CNEOS 22 and 1.2 meters for CNEOS 25. Given the detection of 2 interstellar meteors in the CNEOS Fireballs database over a period of 7 years, the inferred collision rate of meter-scale interstellar objects with Earth is about 0.3 per year. This rate equals the product of the number density of the parent population times the Earth's cross-sectional area, 128 million square kilometers, times the Earth's orbital speed around the Sun, 30 kilometers per second. The measured collision rate yields a number density of 8.4 million interstellar objects of meter scale per astronomical unit cubed, where 1 astronomical unit is the Earth-Sun separation. Shown here, the gold aluminum cover of the Voyager Golden Record on the Voyager 1 and 2 spacecraft protects the Sounds of Earth gold-plated record from micrometeorite bombardment. This implies that there are about 35 million meter-scale interstellar objects embedded at any time within the orbit of the Earth around the Sun. Assuming they have a solid density of a few grams per cubic centimeters, each object carries about 3 million metric tons. Altogether, this population totals 100 trillion metric tons of interstellar materials interior to the orbit of the Earth around the Sun. For comparison, the estimated number density of the parent population of the interstellar object 3I Atlas, which was measured to have a diameter of 2.6 kilometers, is 0.003 per astronomical unit cubed, about 2.8 billion times smaller than the number density of 2-meter scale interstellar objects. The mass of each of these objects is larger than that of a meter scale object by a factor of 2.6 kilometers divided by 2 meters cubed, namely 2.2 billion. Multiplying the number per unit volume by the object's mass, we find that the population of kilometer scale interstellar objects, like 3I Atlas, carries approximately the same mass per unit value as the population of meter scale interstellar objects, about 100 trillion metric tons interior to the Earth's orbit, The fact that the mass density of kilometer-scale interstellar objects is the same as meter-scale interstellar objects suggests that the two populations might be related, with the smaller objects being fragments of the bigger objects, as suggested in the recent paper that I co-authored with the brilliant student O.M. Trivedi. It would be most efficient to study the population of interstellar objects with a new observational architecture, including discovery by the Rubin and Argus observatories, high-resolution imaging by a lunar optical interferometer, and closer studies of anomalous objects by space interceptors. A comprehensive campaign for information gathering would alert Earthlings of potential threats from impacts by either natural rocks or alien technological gadgets. Ignoring threats from the sky did not work out well for non-avian dinosaurs 66 million years ago. So far, our planetary defense strategy contemplated solar system rocks, but we should expand our risk assessments to interstellar objects as well. In the coming months, I will attempt to secure funding for new ocean expeditions to retrieve materials from the two new candidates of interstellar meteors, CNEOS 22 and CNEOS 25. Radioactive dating of their interstellar materials could be used to estimate the durations of their interstellar journeys and constrain their origins. Finding evidence for a Voyager-like meteor would be even more exciting. Here's hoping that in a few billion years, after Voyager 1 and 2 will traverse most of the Milky Way disk of stars, at least one of them will collide with a habitable exoplanet and appear as a meteor to the local population of aliens. Based on its low altitude explosion, a curious alien astronomer might suggest that Voyager is anomalous in material strength based on its low altitude explosion, and potentially it's not a rock. Other astronomers will not only ridicule this proposal, but also deny that Voyager is interstellar in origin by inflating the measurement errors. After leading an expedition to the meteor site, the alien astronomer might find the 12-inch golden record of Voyager with its 115 images, natural sounds, musical selections, and greetings in 55 languages from Earth. Figuring out that they are not alone will be the ultimate intelligence test of the aliens. After all, they must have asked numerous times, "Where is everybody?"